Hi everyone. As we've established, flat earthers believe, or at least claim to believe, that we live inside a giant snow globe. The biblical firmament supposedly keeps the air from bubbling up into the waters above. Yeah, the Bible actually describes the earth as a snow globe surrounded by water. One way they try to debunk the reality that the Earth is actually a globe surrounded by the vacuum of space is by pointing out that if that were the case, the atmosphere would drift away because there's no container keeping it in. Gas pressure requires a container has become a FLERF mantra, just like water always finds its level. So let's talk about gas pressure. This is FLERFPRATT, Flat Earth Points refuted 1,000 times. If you like the video, thumb it up, subscribe, and hit the bell. Before we begin, let me tell you about the sponsor of this video, Brilliant.org. At Brilliant, you can take interactive online courses in math and science. I've been using it for quite a while now, and I've barely scratched the surface of what's available. There are literally thousands of lessons there, with more being added monthly, each with interactive exercises in subjects ranging from beginner level, like everyday mathematics and physics, suitable for those who regret not paying attention in high school, to advanced university level, like group theory, quantum mechanics, and AI development, suitable for people looking to advance their careers. Or if you're like me, you just love learning stuff, or you want to brush up on stuff that's been gathering dust in some dark corner of your brain since you graduated university. I'm really happy I found a place where I can dust it off and even learn some more, and the interactive exercises allow me to do that and, dead serious here, have fun while doing it. The exercises award XP when you get them right, and if you get enough XP in a week, you'll level up to a higher league. This is what keeps me coming back for more, and it motivates me to actually do the exercises instead of just checking the answer and moving on. Active learning like this is much more effective than passive learning, like just reading or watching video lectures. Take it from a professional educator. Use the link below, brilliant.org/Martymer81, and get started on your free 30-day trial period today. The first 200 to sign up using the link will also get a 20% discount on their annual fee. Thank you. Now let's get back to the video. When you blow up a balloon, you create a volume of air at high pressure surrounded by a larger volume of air at low pressure. Poke a hole in the balloon and the pressure equalizes. The balloon pops. It certainly looks like the FLERFs are right. Without a sealed container, pressure equalizes. Ergo, if you have a relatively small volume of air surrounded by a huge vacuum, the air should reasonably spread out to fill the vacuum, creating a huge volume with infinitesimal pressure. So far, this seems perfectly reasonable, but let's see if we can find a problem. Suppose, instead of filling a balloon with air, we fill it with helium. We all know what'll happen now, right? When we pop the balloon, the helium doesn't spread out evenly in the room, which we're assuming is filled with air at normal pressure. The helium goes up, because even at the pressure inside the balloon, it's less dense than the surrounding air. What do we call this, FLERFs? That thing that makes things with low density go up? That's right! Buoyancy! Good, FLERF, remind me to give you a cookie later. And what did we experimentally confirm in the video about gravity and density? Of course, this is where FLERFs who watched it will develop amnesia, because as usual they don't want to understand, but those who actually care about reality will recall the wooden die in the falling cup. There is no buoyancy if we cancel out gravity, because buoyancy is a result of gravity. Oh wait, gas is affected by gravity. So what could be causing the atmosphere to stick to the Earth? Gas pressure requires a container is an oversimplification. It applies to what's called an ideal gas, which, as the name suggests, is an idealization. An ideal gas is made up of particles that aren't affected by any forces other than those that arise when they collide with the walls of the container. Particles never collide with each other and aren't affected by force fields like electric, magnetic, or gravitational fields. Of course, such gases don't exist in reality. It's often a good enough approximation though, and that's where the misunderstanding comes from. For example, the ideal gas law, PV equals nKT, is often used to show how pressure, volume, and temperature relate in gas, but again, as the name suggests, it assumes an ideal gas, so it's just an approximation when applied to a real situation. So can we safely approximate the Earth's atmosphere in its entirety as an ideal gas? Let's see. Let's consider the particles in a container filled with ideal gas at non-zero temperature. Temperature is a measure of kinetic energy per particle, so these particles are bouncing around inside the container, colliding with the walls. As they exert force on the wall, by Newton's third law, the wall exerts a force back on the particles. This is what keeps them inside. This is what gives rise to the pressure. Because we can't keep track of all the particles in the container, we can safely treat the position and velocity of any single particle within the container as being random. Now, think about this. What is the probability of any two particles occupying the exact same location? Remember that ideal gas particles can't collide with each other, so this should be possible. If there are a million places a particle could be, and in a macroscopic container there are a lot more than that, but let's keep it simple here, then the probability is 1 in a million. So what's the probability of all the particles in the gas occupying the exact same location? Well, that would be 1 in a million to the power of the number of particles minus 1. Absolutely negligible. As in, won't happen in the lifetime of the universe if we try once every nanosecond, negligible. By this reasoning, what is the most probable distribution of particles? That's right, an even distribution. So the most likely configuration is one where the pressure is the same in the entire container. This is why pressure evens out. Even distributions are more probable. We say that they have higher entropy. In fact, we explain why the air escapes from the popped balloon with the second law of thermodynamics. The entropy of an isolated system never decreases. That is, a system that has been prepared in a state that is unlikely to occur spontaneously, given the possibility to do so, will transition to a more probable state. A state of more even energy distribution, a state of higher entropy. This is also why a hot cup of coffee cools down in a room at normal room temperature. Okay, so by the second law of thermodynamics, if the Earth's atmosphere is an ideal gas sealed in by the biblical firmament, it will have the same pressure everywhere. Sure, we all know of how the weatherman talks about high and low air pressure, but that's just temporary local variations. That's no problem. It's noise, basically. Particles moving at random won't always be perfectly evenly distributed. But aren't there regions where the air pressure is always low? Why, that's right, at high altitude. Air pressure depends on altitude. The air pressure decreases by about 13% when the altitude increases by 1 kilometer. That's why your ears pop when you fly. I've never heard of a FLERF who denies this, so what we find is that they say pressure requires a container and pressure is higher near the ground, even though there is no container separating the gas down here from the gas at higher altitude. As expected, they can't describe what we observe with an internally consistent model. While we can safely approximate gas in a small container or even in a room as an ideal gas, there's no way we can approximate the entire atmosphere as one and expect to get things right. For those of us who care about reality, that isn't a problem. Gas particles in a gravitational field will bounce around due to thermal motion just like in an ideal gas, but there will be a slight acceleration in the direction of the field, resulting in a greater probability of finding particles further down in the field. This is perfectly consistent with what we observe. A source of gravity in space tends to collect and retain gas. Planets in particular have atmospheres, which are more dense near the surface, and decrease in density exponentially with altitude until it becomes negligible. You don't need a container to have gas pressure. You need a force acting on the gas. Now, that force could come from a container, but it could also come from something else. In particular, The force keeping the atmosphere stuck to the Earth is...
Gravity!
See ya.